that's a kind of different situation. That would be my
Okay. Nice PDF. You could go to the PDF. Preview. Slideshow.
Okay, thank you.
We need to, sorry, we need to set up.
Yeah.
Microphone is still off, I guess.
No, it's not. It's misleading. If it's red, it's off. So this is off. It's on.
Oh, okay.
There are no viewers.
Who is here?
Oh, who is that? Where did you see? Oh, yeah, he's there. Okay. People are joining us.
Who is there?
Who is there? Who is not there?
Okay, just thank people for coming to listen to my talk. So this talk is given as a practice for my defense, for my PhD defense. So please comment when you have any of them. The outline of my research in this thesis is including a study of the background, which includes the observation of the abrupt climate changes. And I will introduce the current understanding of such phenomena. And then my work is trying to separate oceanic and atmospheric contributions in the teleconnection during the abrupt climate change. I'll introduce the model setup and how I identify and compare the two contributions. And I'll analyze the physical process and show the results here. And then a summary of the first part. The second part is going to study the sea surface temperature's role in the teleconnection. I first introduce the motivation and the model setup and analyze the SST's role on the IPCC shift during the abrupt climate change. And show the results here. And then analyze the physical processes that's leading to such contribution. And then the summary of part 2. And finally, a summary of the whole thesis. My presentation starts from kind of flowers here, showing the flower picture. And this flower is called the dryas plant. It grows in environment of glaciers, so it's very cold environment. And this plant has been found to be common in Europe in past climates, which isn't there now. So that indicates that Europe may be colder than now in the past. So how do people discover past climate as we are interested? So here, this figure is showing the ice sheet over Greenland. The Greenland ice sheet is over 300 meters to the biggest one. And there's a ton of information hidden under the ice sheet that's waiting for us to discover. So they are treasures. The people here, these two people here are digging the ice cores over Greenland. And this figure is showing a man that is storing storing the ice core they dig from the Greenland. There are a lot of them, and this figure is showing a sample of the ice core. And this ice core under more advanced equipment is shown here. You see there's 11-year dino cycle here showing. You see there's seasonal variability of the color of the ice core, which indicates different climate conditions in season. In winter season, there's snow, which is whiter, and in summer season, there's kind of dust aerosols that falling down to the ice surface, which make the ice core darker. So people can discover information from these ice cores to discover the past climate. So here is showing one way to retrieve information from these ice cores. So ice is made of water molecules, and water molecules consists of one oxygen atom and 2 hydrogen atoms. And the oxygen atom has 2 stable isotopes. One is the oxygen 16, and another is the oxygen 18. And this number is proportional to the mass of the atom. And according to the temperature equation here, the temperature is proportional to the kinetic energy of the molecule, the average kinetic energy of the molecule. So this heavier one, which is called the nitrogen 18, is heavier than the lighter one. So it had more mass, then it is slower, it's moving slower. So when the ice evaporates, this lighter one tends to escape. Then this heavier one is more lazy and tends to stay in the ice. So the higher temperature, the more strength of the evaporation, then the more this lighter one escapes. Then the relatively more this heavier one stay in the ice. So the temperature can be found to be statistically related to the rate of this heavier isotope. So here it's showing the relation between the two. On the x-axis is the annual average ice temperature, and the y-axis is a linear function of the rate of this oxygen 18. You can see that under 0 degree, there's a very good linear relation between the two. And higher than 0 degree, the relation is worse, because higher than 0 degree, the ice becomes water, and water flows around, so it messes up the relation. So the rate of the oxygen 18 isotope is a very good proxy to discover the past temperature using the ice core. And here's what people discovered from the ice core they dig from the Greenland. And here this figure is showing the past around 15,000 years temperature over this Greenland site. You see that there's smaller wiggle in the past 10,000 years, and there's a big abrupt change in this period, which is called the younger dryas. And at this period, the dryas plant was found to be common in Europe. You see, at the beginning and the end of this period, the change is very sharp, and these changes are called the abrupt climate changes. And people retreat more further to the 50,000 years. You see, there are a lot of more wiggles here, which indicate that in the past, at least 10,000 years ago, there are a lot abrupt climate change in the Earth. But recently, there's not much here. Here is showing the temperature difference from today at the younger dryers, and these information are discovered in other sites. Here, the cooling in the Greenland are discovered by the article I just introduced, and here the stronger cooling around North Atlantic Ocean at the coast region, and here is the cooling in the over the Cariaco Basin. This is reflected from the sediment discovered there. And here is the cooling people found by using the data from the Hulu cave in China. So basically, the northern hemisphere is cooled in the younger dryas period, and the southern hemisphere is vague. So let's see what sediment record called. And the sediment records have been found in Cariaco Basin, which is to the north side of the Venezuela, and it is around 10 degrees north. So here is a sample of the sediment, and here these people are freezing the sediment sample using the liquid nitrogen, and here's a closer view of the sediment sample. You see that there's cycle here. Here the layer is darker, and here is darker, and here is darker. These indicate the annual cycle of the sediment, and this indicates a seasonal variation of the local climate. And the advantage of this basin is that this basin is very well protected from the western boundary current by the higher topography around this basin. So the sediment is not affected by the general circulation. So it can very well be used to retrieve the past climate, local past climate. And in summer, this 10 degree is around the ITCZ, the northern hemisphere ITCZ, and it's rainy in summer. And in winter, the ITCZ moves to southern hemisphere, and here is where the trade wind blows. And trade wind blows against the coast and carry out nutrition from the bottom and feeding plankton. And plankton is lighter, and it sinks to the bottom and forms the layer of the sediment, which is lighter because of the plankton. So this forms the annual cycle. Now here this line is showing the past gray scale of the sediment. You see that over the younger dryas period, this gray scale is lighter, which indicates that at this period, there's more plankton sinking to the bottom, which indicates that there may be stronger trade wind over that period. The stronger trade wind may be because of the southward shift of the southern hemisphere ITCZ, or strengthening of the southern hemisphere ITCZ, or it may also indicate a southward shift of the northern hemisphere ITCZ. So what controls the climate over Greenland? Here's a scheme. Here's a mechanism that is generally believed by researchers. But around Greenland, which is subpolar Atlantic and the Arctic, there's strong deep ocean convection, which is caused by the North Atlantic current, which bring salty and hot water from the lower latitude to the subpolar Atlantic Ocean, and the water becomes colder as it reaches the subpolar Atlantic Ocean, and because it's salty, and then it sinks to the bottom, which induces the deep convection. And this thinking, the thinking of this water is replaced by the warm water from the south, which keep this area warm. But if for some reason the sinking motion is reduced, then the cold water is accumulated here, then make the climate here colder. So what mechanism is possible to reduce the sinking? One, we first know that the salty water sinks. If it's freshened for some reason, then this sinking motion is reduced. And another mechanism for sinking motion is that here in the subpolar Atlantic Ocean there's sea ice, and at the bottom sea ice, when the water freezes into the ice, the sea salt was kicked out, and making the surrounding water salty, and surrounding water will sink to the bottom. But both of the mechanisms are affected by the freshening. So let's see whether there is freshening in the past. Here is showing the past topography in the Northern American. You see that in the past 1,000 years, there's a very wide North Atlantic ice sheet, and this ice sheet is connected to the Greenland. You see that it retrieved gradually, and becomes more or less the same as they in around 5,000 years ago. And when this North American ice sheet retrieved, the meltwater may flow into the North Atlantic. And this is the case people haven't found evidence yet. But they approximately calculate the area of Northern American ice sheet using the data retrieved from the glacial, from the geological records. They calculate the area of the ice sheet and assume that the height is conserved. Then assume that all the meltwater flows into the St. Lawrence River and then flows into the North Atlantic Ocean. And this fresh water can be carried by the North Atlantic currents flowing here into the subpolar North Atlantic. Now here is showing the retrieved freshwater flux. You see that this freshwater flux is consistent with the period of the Greenland temperature dropping at the Younger Dryas period. And afterward, there's another flux. So this flux didn't trigger any abrupt climate change. One possibility is that the ice may not only flow into the St. Lawrence River into the North Atlantic, but it may also flow into the Arctic Ocean from here. And other possibility is that the water may be stored on the land, forming the Great Lakes here. So this is not a complete evidence showing that a freshwater flux source is found. But people can use a model experiment to simulate such freshwater hosting. You see that at subpolar North Atlantic Ocean, the uniform freshwater is hosted into this area to simulate the freshwater from the land. You see, this is the St. Lawrence River, and the North North Atlantic currents flow here and bring the fresh water into this region. The amount of the fresh water added into the model is around 0.6 Sverdol, and they do two experiments. One is control, another is hosting. So this run is by link. Control run. The experiment consists of a control run which is 400 years, and the hosting run which is 60 years, with a sample number of 5. So this is showing the response of the response to the hosting of the surface temperature. The surface temperature normally is averaged over the 6 decades after the fresh hosting. And the hosting is continually. You see that this area is a hosting area, but there's global climate response to the hosting, regional hosting, including broadly cooling in the northern hemisphere and broadly warming in the southern hemisphere. And there's much more detail, like here that the coast town, and there's smaller warmer spots over the northern Atlantic Ocean. This is showing the precipitation response. Clearly, you see that the Atlantic Ocean, the Atlantic ITCZ is shifted southward. The North Atlantic precipitation is reducing, and South Atlantic Ocean is increasing, which indicates a southward shift of the ITCZ. And the Cariaco Basin is here, and this is consistent with what people discovered in the past over the Cariaco Basin. In the Eastern Pacific Ocean, the ITCZ also shifts southward. In Western Pacific, it's a little complicated, and the ITCZ, the precipitation decreases a little to the south of the equator, and in the Indian Ocean, there's an increasing of the precipitation in the southern tropics, and at the area where the hosting is applied, there is also decrease of precipitation, which is probably the snowfall. And so, because the ocean and atmosphere coupled system takes thousands of years to reach equilibrium, so we are not confident yet that the sixth decade reflects the equilibrium response. Here it's showing the same figure as previous in the six decades normally, and here's another figure showing the same, but the third decade normally. You see that the patterns of the surface temperature normally are basically the same. There's cooling in the northern hemisphere and warming in the southern hemisphere, and there's detail like this cold town here is shown, and small spots warming at here. They're all the same at 2 decades, and the precipitation is also showing the same pattern. You see that at the freshwater hosting area, you see the decreasing of the precipitation, and there's a southward shift of the Atlantic ITCZ and the Eastern Pacific ITCZ, and there's a decreasing of the South Tropical Western Pacific. So to see the time series of the temperature anomaly and the precipitation anomaly give us more confidence that equilibrium state is somehow reached. So this line is showing the surface temperature normally averaged over northern hemisphere, and this line is showing the surface temperature normally averaged over southern hemisphere. You see that the northern hemisphere temperature already the transition of the change takes around 20 to 25 years, and then afterward it is more or less stable. And southern hemisphere is difficult to see, but it's not changing much. And this is showing the same, but for the precipitation normally. You see that at the first 10 years, the change is sharp. Then afterward, it changes, but the magnitude of the change is not much. And the southern hemisphere is more gradual. So this indicates that the sixth decade, which is around here, more or less reflects the equilibrium response to the whole thing.
So those those are dashed lines, or is there any break in data?
Dashed line are the same as the step
Are they dashed lines, or is there any break in data?
breaking data.
Just
Dashed
dashed lines.
These are models, so there's no missing.
So I mean,
Oh.
then that probably is very difficult to see. If it is time series, you could use different colors.
Okay.
So those magnitudes are really tiny, and you can't see them with the dashed lines.
Oh yeah, it's a little misleading. Right?
The same with the bottom panel too.
Yeah. Yeah. Thanks. So this figure is showing the ocean circulation change. This shown here is the Atlantic meridional overturning circulation anomaly averaged over the 6 decades, and the lines are showing the control, which is the climatological value, and the color is showing the anomaly. You see that in control there's a clockwise overturning circulation if you see from the east, which means that the warm water at the surface flows northward and sinks in the subtropical area and then flows back to the south at bottom. Now here is another small circulation. You see that the anomaly is negative, which means that this Atlantic meridional circulation is reduced, and this is consistent with what the mechanism of the Atlantic meridional of the sinking motion affecting the subpolar climate scheme. And here it's showing the atmospheric general circulation. You see that the lines are showing also the control values, and the color is showing the anomalous values. You see that in control there's a upward flow at the equator, and this upward flow flows the two-way to north and south, and then sink to the surface and then comes back. So this is the Hadley circulation in the tropics, and the anomaly is basically in the around the equator, and it's positive, which means that there's an extension of the northern branch of the Hadley circulation to the south, and the squeezing of the southern branch of the Hadley circulation to the south too. So this indicates that the center of the Hadley circulation is shifted southward. So this figure is showing the anomaly of the northward energy transport. The real lines are showing the atmospheric transport, and the dotted line is showing the oceanic transport. And this red color is for the hosting experiment, and this black color is for the control experiment. So comparing the two atmospheric heat transport, you see that the hosting experiment, the atmosphere transport more heat from south to north. And when you compare the two oceanic heat transport, you see that the red is lower than the black, which means that in the hosting experiments, the ocean transports less heat into the north, which is consistent with the atmospheric and ocean meridional circulation. Because the reduction of the meridional overturning circulation reduces the oceanic heat transport, and also the southward shift of the highlight circulation reflects the increasing of the northward energy transport at the equator. So people have proposed different scheme to explain the teleconnection between the regional freshwater hosting and the global climate response. But this schematic figure is showing one of the mechanism. You see that this mechanism says that the reduced overturning circulation is not dominant it's domination of the teleconnection. The first the reduce of Atlantic meridional circulation induces anomalous southward heat transport by the ocean, and this southward ocean energy transport make the northern main latitude cooler and make the southern hemisphere warmer. But the cooling in the northern hemisphere increases the surface temperature gradient, and the increasing of surface temperature gradient increase the atmosphere baroclinic instability, and this baroclinic instability leads to more eddy heat flux from the south to north, and this eddy heat flux cools lower atmosphere, and the cooling of lower atmosphere also introduces higher surface temperature gradient, which introduces stronger trade wind, and stronger trade wind blows the moisture from the north to the southern hemisphere, and this moisture feeds precipitation in the southern hemisphere, which induces the ITCZ to move south. And within the ITCZ clouds, because the moisture release heat to form rain and make the troposphere warmer, and the warmer of the troposphere decrease the surface pressure, which in turn increases the surface pressure gradient, and then stronger trade wind blows to south. So this induced circulation can maintain itself, and there's no need to change so the surface temperature is a side effect of this induced circulation. So this is one story. Another story is that people found that without any oceanic circulation change, without any oceanic dynamics, there's also teleconnection between the freshwater hosting and the remote climate response. And this scheme is showing that the cooling induced by the freshwater change the surface temperature, and surface temperature gradient change leads to more eddy kinetic energy, more eddy heat transport. This is the same as the previous, and the increasing the eddy heat transport drain heat from the lower latitude, and this draining of heat from lower latitude requires more heat to drain from the surface and more further lower latitude. And this process goes on and propagate the cooling originating from the subpolar to the equator. And the cooling over the northern hemisphere, northern equator increases the pressure and increases the trade wind, and then shift the ITCD southward. So this is another story. So one story is showing that the ocean is playing the dominant role. The other is showing that the atmosphere is playing the dominant role. Okay. So, but the previous atmospheric dominant scheme is missing a lot of processes. For example, when the ocean is cooling, it induces the surface wind is also changed. The surface wind can change the wind-driven circulation in the ocean, and this anomalous circulation in the ocean can in turn affect the surface temperature, then in turn affect the atmosphere. So the feedback from the ocean is missing. So my question is, since people argue that both atmosphere and ocean play a role in the tidal connection, so what's the relative importance of the two components? Let's see first the equation of the surface temperature as an example. So supposing that the ocean mix layer doesn't change, and then the surface the temperature, the rate change of temperature over time of the ocean is decided by the oceanic heat flux and the surface heat flux. The oceanic heat flux is precisely the oceanic heat flux divergence averaged over the mix layer. So it's called the heat flux, but it's actually the heat flux convergence and the surface heat flux. You see that in this equation, both the oceanic heat flux and the surface heat flux is functions of temperature and also other variables, because both of them are very complicated. And the atmosphere can affect the ocean by changing the wind, not only the SST but the wind, and the ocean can affect the atmosphere only through the SST. So the three of them are coupled, tightly coupled. When we try to identify the contribution from the atmosphere and the ocean, this equation cannot be used because they're coupled. When you eliminate one of them, the other two change. So we have to find a way to eliminate one of them and see what the pure other one is contributing. Here's the model design. So this is a box showing that I have a model, and using this model, I want to, in one way, to mimic the fully coupled model. And in this, because once I can mimic a fully coupled model, and then this experiment, in this experiment, both the atmospheric and the oceanic contribution is included. And in the other way, I can simulate with ocean dynamics eliminated. And in this way, only the atmosphere is contributing. And the two in the two simulation, the forcing is the same. And one is including both contributions, and another is including only the atmospheric contributions. Then the comparison between them can show the oceanic contribution. So I use slab ocean model. The advantage of slab ocean model here is introduced here. So the ocean consists of 3 layers, including the mixed layer, the thermocline, and the deep water. And in a fully coupled ocean model, all of the ocean dynamics is active. The ocean exchange energy, water, and momentum with the atmosphere, and there's entrainment, there's interaction between the mixed layer and deep ocean and thermocline, and there's mixing. But in the slab ocean model, it consists only of a mixed layer. There's no deep ocean or thermocline, and this is stable. There's no motion in the mixed layer, and it exchanges energy, water, and momentum with the atmosphere. But the water and momentum exchange is only one way, because the slab ocean doesn't lose or gain water or momentum, but the atmosphere is affected by the ocean. So you see that in this model, there's no ocean dynamics here. So I can use this model to eliminate the ocean dynamics. And because the deep ocean, the ocean dynamic is eliminated in the slab ocean model. So there's missing part. There's missing part in the model. As an example, you see that the max layer temperature, the relative change of max layer temperature is decided by the advection, by the ocean advection of heat, and the cooling by Ackermann upwelling, and the cooling by entrainment, and the surface temperature. In the slab ocean model, all of these are eliminated. So I have to artificially provide these data to the slab ocean model, and this data is called the Q-flux. You see that Q-flux consists of velocity, and ocean velocity is affected by the atmosphere, and also the upwelling is also affected by the atmosphere. So Q-flux is actually an interactive term. But here in the slab ocean model, because there's no such interaction, so Q-flux here is prescribed in the slab ocean model. And the Q-flux, since I want to mimic the fully coupled model, the Q-flux must represent precisely this term in the fully coupled model. But in the fully coupled hosting model, hosting simulation, these terms are not calculatable. So I design a technique called the SST restoring technique. The detail of this technique is introduced here. The original equation of the temperature in the slab ocean model is given here, like previously shown, and I add an additional damping term to this equation. And this damping term, you see that it's proportional to the temperature difference between the temperature and the prescribed temperature. So this term ensures that this temperature is always more or less the same as this prescribed temperature. And because the ocean only affects the atmosphere through SST, so this surface heat flux can be the same as the flake couple model if surface temperature is the same. Then we can conclude that the Q can be the same, or Q plus this term can be the same. So I simulate using this equation and prescribe this temperature as the temperature in the flake couple model. And then if this surface heat flux is also the same as the flake couple model, then I can save this Q plus this damping term to be the Q flux, and this Q flux must be the same as the oceanic heat flux in the flake couple model. So I did the simulation to calculate these Q fluxes, and I don't show here because the time limit. And I use this Q flux to run 3 sets of experiments. One is called the control simulation and hosting simulation. These two are going to mimic the fully coupled control and hosting simulation. And then I run additional simulation where the hosting Q flux is applied in the hosting area, and the control Q flux is applied elsewhere. In this way, the Q flux perturbation is only applied in the subpolar North Atlantic Ocean.
So one question: the Q flux normally has a property the global mean is 0, right?
Yeah.
When you do this partial, do you enforce that?
Yeah, because the deep ocean takes thousands of years to respond. So when you host the ocean atmosphere system, there's no conservation of.
So your Q flux global mean is not 0.
No, not. Even you average this one, you can see from eyeball that the average is not 0. And this Q flux is directly induced by the fresh water. So we can say that the 2 experiments are responding to the same freshwater hosting. And because in one simulation, the Q flux perturbation, which represents the oceanic heat flux perturbation, is kept in lower latitude. In another, is limited. So and because this simulation mimics the flake couple model, so both oceanic and atmospheric contribution are included in this one. And in this one, only the atmospheric contribution is included, because the oceanic response is eliminated. So let's first check whether Q flux is calculated successfully, so that we can use them to mimic the fully coupled model simulation. The key is showing the comparison between the chemistry control and the fully coupled control simulation. But this is wrong. This is 100 years. This is 400 years. Sorry. And you see that these two are basically the same. You see that there's a warming bears at here. There's a double warming at the Pacific, tropical Pacific. And to quantitatively show that they are the same, I gave the root mean square of the difference between the two, and it's around 0.4. It's around 0.4 Celsius, and global mean standard deviation is around 4, so it's 10 times. So we are confident that the annual average of the fully coupled climatological surface temperature is reconstructed by using the live ocean model.
Norman, I thought I heard you say 0.4 and the slide says 4.
Yeah, I'm sorry. This is the wrong place. I should have shown this one in another place. I'm going to change it.
So which is it?
This here is 0.4 Celsius, and here is 4 Celsius.
I think this meant to be a surface heat flux. When you put
yeah.
the surface heat flux value into the SST, you simply the wrong thing. You're just mistaking your label.
This SST, I thought it was SST, then I thought it's flux.
Yeah.
I'm totally
No,
confused.
Yeah, I'm sorry.
SST.
Yes, and this
Those
is
numbers actually
this is
meant
400
flux.
years, and this is 100 years.
But they just got the two things messed up.
So what is the RMS difference for the SST?
RMS of difference is 0.4 Celsius. And the global mean standard deviation is 4, so it's 10 times difference. And then the annual mean surface temperature is reconstructed. I'm going to show the annual cycle of the surface temperature. You see that this is an average annual cycle of the CAM3 control, and this is the CSM3 control. And the annual mean is eliminated. You see that the two are basically the same.
Why do you say this is reconstructed?
Reconstructed
How do you reconstruct it?
by using the Q flux I calculate.
Or would you rather
Oh,
do
no,
the
that's
simulation
what
with
you
the
mean,
Q flux? Or would you do
Yeah.
the simulation?
You can just say simulated.
Sim-
It's not really reconstruction. Normally meaning
Yeah.
Reconstruction
proxy or
of
something. You use the reconstruction, but that's not what. We don't use this word for our field.
So it's mimicking.
So for CAM3, you use relaxation or you use fixed SST to compute the Q flux? Use relaxation.
Here relaxation.
So if you use fixed SST, you'll reproduce the climatology exactly, right?
Exactly.
That's
Yeah.
the reconstruction.
But here I don't use any damping term because I already compute the Q flux. Then
So you don't use the damping term
Yeah,
there.
I already had the Q flux.
So that's just climatology then?
Yeah.
Except for sampling issue.
Yeah.
You can see that the annual cycle is pretty much assimilated. See that in non-hemisphere, in summer it's warm and in winter it's cold, and in southern hemisphere it's versus. So this is consistent with what we observe. And this is showing the surface heat flux assimilation. You see that this CAM3 control experiment control is annual average almost the same as the CSM3 control. You see that in the over Pacific there's strong surface heat flux, and at the western boundary because the ocean is very warm, and the surface heat flux is big. You can see here. And the RMS is computed is 4 watts per meter square, and the global mean standard deviation is 30. So it's around 8 times difference. Then the assimilation of the annual cycle of the surface heat flux. You see that the annual mean is also eliminated, and the x-axis is the 12 months of the year, and the y-axis is the latitude, and zonal mean is taken for ease of view. And you see that in the two figures are basically the same. In the non-hemisphere, in the summer in non-hemisphere, the ocean the atmosphere and the surface heat flux is into the ocean, and in winter is into the atmosphere, in summer it's into the ocean, and in winter it's into the atmosphere. And in southern hemisphere is the worst situation. So we look at this equation again. We see that both temperature and annual cycle temperature is assimilated. So we are confident that this rate of change of temperature is assimilated. And we also have the same Q, or the same F here, the surface heat flux here. So we are confident that our Q flux, our climatological Q flux, is the same as the oceanic heat flux in the fully coupled CSM3. Now here I show more figure to convince that the climatology of the fully coupled model is mimicked.
I'm convinced.
Okay. I'll skip these. Here I show the hosting simulation. These figures are showing the surface temperature anomaly, and the top two are showing the CAM3 simulation, and the lower two is showing the CSM3 simulation, and the left two are showing the second decade average of the anomalous surface temperature. You see that if you compare the two, the patterns are basically the same, and the cooling, broad cooling over the northern hemisphere, and much detail like the cooling over the subtropical North Atlantic and warming spot area. And this is showing a half-molar diagram with x-axis the time after freshwater hosting, and the y-axis is the latitude, and zonal average is taken. See that there's a propagation of the surface cooling from the high latitude to the lower latitude. And it takes around 7 to 8 years for the cooling to reach equator. And in the fully coupled model, it's the same thing. You see that the cooling originating from the high latitude propagates to the equator and within around 7 to 8 degrees and stop there. So basically, the hosting experiment is also mimicked. So now we can say that the first hosting experiment using the slab ocean model can mimic the hosting simulation using fully coupled model. Then in this simulation, both the atmospheric contribution and the oceanic contribution is included. And in the other hosting simulation using the slab ocean model, because only the atmosphere contribution is included, then we can show a figure here. And this is showing the same thing as the previous, but showing more. And in the top is the fully coupled hosting simulation, and the second is mimicking the fully coupled hosting simulation using the slab ocean model. The third one is the simulation where the Q flux is eliminated elsewhere except the North Atlantic Ocean. And the last two figures are the difference between the two. So we can identify that the top and the second are both include the atmosphere and the ocean and contribution to the teleconnection. And third one is representing the atmosphere contribution. And last one, because it's the difference between the total and the atmosphere, I can say that this is the oceanic contribution. as long as the atmosphere contribution and the oceanic contribution are linearly add up together to make the total contribution. You see that these two are still similar as I have shown previously, and there's a propagation. So this time x-axis is latitude and y-axis is the time after fresh water. You see that there's a propagation of surface cooling. The propagation of surface cooling, the Flatbush model. And the oceanic contribution, the atmospheric contribution is also propagating the surface heat, surface cooling southward. But the oceanic contribution doesn't show the same propagation. The cooling stops at around 20 degrees. But the ocean seems to be much faster. You see that at the very beginning, the ocean already contributes warming at the tropics. And this has been shown in Ping Chang's paper that the ocean induces warming in the equatorial Atlantic Ocean very fast. And you see that the atmospheric contribution is more or less more
This is the
zonally symmetric.
This is globally zonally average? No.
This is zonal average.
Globally zonal average.
Globally.
I mean, it's not only for the Atlantic sector. I mean,
No, it's not.
All oceans.
for all oceans.
Yeah.
That's really strange. The ocean goes faster than the atmosphere.
He said you showed that already.
It's not true.
No, but I think if the thermohaline circulation, the question is how fast does the thermohaline circulation change, propagate, right?
And what we showed was that the atmosphere leads, and then the ocean actually kicks in 20 years later.
Yeah, it's 20 years in the GFDR model, but in this model it's faster.
But it's not faster than the atmosphere process. I don't know.
Yeah, it's hard to believe it can be instantaneous.
There's no way. I mean, unless there's something with the initial condition.
I'm worried about your global mean, because your global mean is changing instantaneously. Right? And your global mean isn't zero in your Q flux.
No, it's not zero.
Mean is changing instantaneously.
Yeah, and this may also be due to natural variability.
But you can deal with statistics. The statistics should tell you if it's statistically significant.
This is significant if a test.
Then it's not. Then natural variability is taken out. Right? Some sense, depending on how you do the tests.
The atmospheric contribution is more symmetric than the oceanic contribution. You see that this cotton is actually dominated by the oceanic contribution, and the small size where it's formed at the western boundary is actually the oceanic contribution. And this warming area is where the
I think this probably comes from the fact that we only have 5 ensemble in the
5 times 20.
5 ensemble hosting runs, and we sample the things. We use 5 different ocean initial conditions. So when we add it up,
This is not the same ocean initial.
it's not the same ocean initial condition.
Oh, that could be a problem.
So when you do the
Yeah,
5
so you just have
ensemble,
5 degrees of freedom.
exactly. So you're not eliminating all the internal variability.
If you do the same ocean initial condition, you'd be better off.
Right. But in this case, because we're trying to sample through the AMOC response,
Right.
so
Okay,
we're
that
trying
could
to
explain.
that's probably
Then
the
it's
reason why
ocean
you
natural
see
variability.
the initial thing.
and the southern
So I
hemisphere.
would recommend you not discussing this because the propagation features, because there's going to be definitely contamination from the natural variability here.
What are those? So if you look at the Hormona diagram, there's like, so there's a much higher frequency variability.
That looks like annual.
Just
I think it's just the natural variability of the couple system. Which one? The 40 couple model?
means in both you see.
In general, you see,
Yeah, it's probably just the natural variability of the ocean. I mean, there's El Nino and things like that in the
yeah,
model.
it could be.
If you only have 5 ensemble size, you're not canceling the model.
You're not canceling it out. It's much. It's like in the previous slide you showed it. On the previous slide, it looked more easier to look at it.
Yes.
That's clearly the annual cycle there.
Okay.
There could be some annual cycle residual too.
Yeah, it's a residual.
Modulation in the annual cycle.
Aliasing of the annual
Yeah,
cycle.
not canceling out.
So your main result is that the column 3 looks like column 1. Sorry, row 3 looks like row 1.
The row 2 looks like row 1.
That's just, you're just setting up the model there.
Because the
Row
slide-
2 looking at row 1 is validating the model, and row 3 looking at
Yeah.
row 1 is the result.
row 2 is like row 3.
Well,
yes,
I mean,
similar.
I think his point he's trying to make is that the ocean does make a contribution because the amplitude you actually see. I think the picture on your left still is valid, right? Because you're taking the time average here too.
Yeah, this is
So
second
those
decade.
fluctuation would actually cancel out when you take the,
Oh, okay, yeah, that's time average.
right? It's a time average. So only this time evolution is it's probably not very useful.
Yeah.
But there's too much variability in it. But I think the time average is still okay.
Okay.
And these warmer spots which is associated with the western boundary current, because the western boundary current, the location where western boundary current leave the continent coast is very sensitive to the ocean condition, local ocean condition. So it's reasonable that this is the ocean and contribution. And in this figure, it's showing the same thing, but the precipitation response. You see that in the fully coupled model, the fully coupled model is very well reproduced by the slide motion model. See that a southward shift of Atlantic ITCC is reproduced, and increasing over the equatorial Pacific Ocean, and the increasing of precipitation to the north and south of the equatorial Pacific. They're all reproduced. And in the Indian Ocean, there's increasing of the precipitation is also reproduced. And the atmospheric contribution is more zonally symmetric than the oceanic contribution. See that in northern tropics, the precipitation decreases, and in the southern tropics, the precipitation increases in all of the three basins. But in the ocean, the oceanic contribution it shows much more detail. That in the Atlantic Ocean, it simply increases the tropical precipitation.
Can we briefly go back to the previous slide and then come back? So is there an signature, El Nino-like signature in the SST that's responsible for the ocean?
Yeah.
El Nino.
In the ocean part. Go back to the SST.
Yeah, this project on
These are El Nino.
that's
Right.
giving you the ocean response.
That's right. Okay, that's the reason why you're getting a zonal asymmetry.
Okay.
Well, these are two
Could probably omit
mathematical.
though, they're distracting.
This one, I think, just
Just
really
leave it out.
eliminated.
It's
It's
too
just
noisy.
like a completely noise.
Yeah.
You don't get any sense of this.
I leave it to show you that the natural variability of the
Okay.
precipitation is much more bigger than the surface temperature.
I think it'll save you time, because if you show it, people will ask about it.
Right. I don't think you should show
Just
this.
leave it out.
And
Just
that's not
say
the
it's
point of
noisy,
your-
that's all. Just say it.
This is showing the box plot of heat transport anomaly accumulation, and it is averaged over the second decade. The unit is 10.24 shower. You see that the top is the fully coupled model simulation. The second is including both the total and both the atmosphere and oceanic contribution. And second is only showing the atmosphere contribution. You see that this total contribution mimics the fully coupled simulation. And this fully coupled is only showing the atmosphere because the ocean part is not calculable. See that there's northward heat transport in the atmosphere and in the atmosphere here, and at high latitude there's freshwater induced ocean heat flux, and here there's surface heat flux induced. And here in the mid latitude, there's downward anomalous heat flux. And in the non-tropics, there's upward anomalous heat flux.
So how does this picture compare to that picture you showed earlier by John Chen? Did you take a look at that?
Yeah, they are showing basically the same as this figure. They're showing only the atmospheric contribution. And if you compare the atmospheric contribution to the total contribution, you'll see that the ocean actually plays a role in changing the heat budget. See that in the atmosphere contribution, the surface is cooled by the atmospheric heat transport, and this heat transport requires heat from the top atmosphere. And the ocean actually induces local circulation here. The energy is transported upward and even up to the top atmosphere, and induces northward heat transport by the atmosphere in the mid latitude here and downward here. So there's kind of oceanic induced circulation here.
So I think if you're comparing that the middle panel with the bottom panel, I think the largest, in terms of the atmosphere, the horizontal heat transport, right? The largest difference is probably occurring somewhere around 30 degrees north, right?
Yeah.
So in the case you have the ocean, you're actually transporting much bigger heat northward.
Yeah. Yes. So this is what the oceanic induced.
So I think the bottom picture is more consistent with John Chan's argument, where he shows this transport actually decreasing as you go from the northern hemisphere to the southern hemisphere.
Yeah, this is consistent with the second scheme.
Consistent with this picture. Right? But then if you include the ocean into it, then you don't see this monotonic decreasing transport anymore. You actually see a local increase of the heat transport somewhere 30 degrees north.
Could you back up a minute? You haven't made any comment on it, but the boundary fluxes are substantially different there. In connection with Ping's comment about what's happening in around 30 degrees, you see that greater transport around 30 degrees than in the atmospheric contribution is consistent with the reverse in direction of the surface fluxes.
Yeah. In the mid-latitudes.
The vertical fluxes, yeah. See, when the ocean's there, there's a lot more heat going into the ocean. And as far as the atmosphere-only simulation, there's heat coming out of the ocean. Right?
Yeah, can I talk to you later about, I think it has more to discuss. So this is showing the eddy activity in the high latitude atmosphere. I have shown that the mid latitude transports more, the atmosphere transports more heat in the mid latitude, and this is showing that the eddy activity these figures are showing the activity. You see that in the northern mainland highlight shows the activity is increasing in the whole simulation.
So your northern hemisphere is on the left side now?
Yeah, it's on the left side because of
Jesus,
this.
okay.
It's the GFDL style.
Yeah, depends on.
The GFDL used to do that all the time.
Really?
Yeah. But
Yeah,
nowadays
I didn't-
plots have,
I didn't have time to replot these figures. When I define them, I'm going to replot and show the north to the right. And these light figures are showing the heat transport by the atmosphere, the transient eddy heat transport, which reflects the heat transport by the eddy activity. You see that at the lower atmosphere, there's huge amount of heat, anomalous heat transported to the north. This is consistent with the box plot. So to determine how the atmosphere cools the ocean, I showed the figure here. And the surface heat flux anomaly is contributed by four components, including the latent heat flux, central heat flux, clear sky radiative flux, and cloud radiative forcing. In mid-latitude, you see that the surface heat flux cools the ocean, and this cooling is mainly contributed by the surface sensible heat flux, and minusly by the clear sky radiative flux.
so latent heat flux is not an important player.
No, latent heat flux is actually
That's surprising because especially in low latitude, you think latent heat flux dominates.
Yeah.
in low latitude, latent heat flux actually dominates.
Even mid latitude, it's not the biggest.
No, mid latitude is not. And you see that the clear sky radiative flux is the anomaly is upward, which means that the surface air is cooling much faster than the surface water. So this and the surface sensible heat flux is also contributed by the air sea temperature difference. In the tropics, you see that the cooling of the surface ocean is mainly contributed by the latent heat flux, and also minorly by the clear sky radiative flux. And this is contributed by the strengthening of the trade wind. Here is showing why the sensible heat flux, how the sensible heat flux is changed. You see that the nominal sensible heat flux is dominating in the high latitude North Atlantic Ocean, and then this anomaly is linearly separated into the contribution from the air sea temperature difference, and due to the surface wind. You see that it's actually the air sea temperature difference that contributes to the sensible heat flux in the mid latitude, and not the surface wind. So this explains also why the latent heat flux is not dominant, because the surface wind almost doesn't change the sensible heat flux. So it is the atmosphere first is cooled by the eddy activity transporting heat from south to north. Then the cooled surface air cooled the ocean surface in mid latitude by directly contacting and by radiation.
You want to move the second row to the bottom row. It's very confusing to have it in the second row. It's addition of the next two things I'm going to show.
Yeah, I'm going to report this one.
It's the addition of the about.
Yeah, it's like actually Python scale. It's Python style, because the zero it comes from 0, but I'm comfortable with counting from 1. So it's, so as to the oceanic contribution.
Back up, please, to put another perspective that supports this. If you, instead of saying addition of next to, that's not
The class of next to.
No, you would explain the top, then you're explaining row 3 and row 4, and then you're going back to row 2. That's the sequence is all.
Oh, how many more slides do you have?
that's
It's almost 6 o'clock. People
Yeah.
needs to go home.
We started late, but I think my comment is your introduction is way too long.
yeah.
Your introduction is way too long.
It's a good introduction, you had a lot of nice slides, but it's just,
Yeah, could you back up 2 slides?
Back up.
3. This is a really interesting slide.
Yes.
And this occurred 1 hour and 10 minutes after you started.
and it's also a very hard slide. You might want to draw something. It's,
Yeah.
it's
I mean,
difficult to see where to focus on.
I mean, how to.
So-
Because this slide
Draw
has
the
lots of information in here. You really need to explain what this means.
What you can do is draw ellipses saying, look at these two and then these two, compare.
Right.
So I didn't need to, I don't know if it's time to make this comment, but I didn't need to see the ice cores and see little layers in here. I didn't need that. I needed to understand this.
Okay.
I mean, if you have, devote like a third of your talk to the introduction and then 2/3 to backend
Right.
discussion.
And also, this comparison, verifying your technique is working. You don't need to show 10 slides just to make your point.
Yeah.
I mean, you can do that in your thesis, but not in your talk.
Just a couple of slides.
It's just 1 or 2, that'd be more than enough.
And if the people have questions, you can bring out the other slides and show it to them.
So how many more slides do you have?
It's not even go through 1 chapter yet, so then another chapter to show.
Oh.
Yeah, it's going to go another hour, I think.
Oh,
Yeah, it's around 20, around 10 over 10, I think.
Yeah.
Yeah, I can skip it.
You could also, so you have a lot of pictures where like the both runs, SCAM and CCM, they're not showing any differences.
Yeah.
You could just mention those and highlight only the where you see the difference. Where you have some results.
You can show 1 or 2 of them, then
Yeah.
see
He's
that.
saying you could show one, and you could say, I could show you the other one that looks the same.
Okay, thanks.
How many more slides do you have?
Over 10, I think. Yeah, I want to skip the first
Somewhere.
part. So then the question, can I have 10 more minutes, please?
This is the heart right now. This is the heart of your talk.
The second part.
And it's already come to the point where the audience is in rebellion.
When is your defense is in March?
Nice.
Who's talking next week? Do you want to just borrow some time?
Maybe you can borrow her time and then do another run, because this is way too long.
Yeah.
We need to go
Can I
over
just
with you and
talk
make
to you?
sure.
Yeah, but say if you have 45 slides, no more than 15 slides to finish.
There's no. Well, we need to discuss whether we can actually do this. Let's meet next Monday. And I don't think there's a point that draft is on.
Yeah, and I need to delete some of them and emphasize
I mean,
more
you
on
need to
the.
select what are the important slides and what you need to show. If we decide to go through this.
But also your punchline, it's good to mention it in the beginning, mention it in the middle, and also mention it in the end.
Right.
Getting to it, I still haven't heard the
Right.
punchline.
I was thinking that my introduction should be interesting to the people, so that's why I did.
No, when you give the introduction, it's like a lecture in a paleoclimate
Right.
course. That's not.
Yeah.
It's not. You have very nice slides.
Yeah, some of the things I really like, but it's you need to control your time. You don't want to spend more than half of your talk giving your introductions, right? I mean,
Yeah. Okay.
I mean, you can do that to a high school teacher or something like that, but
The intent is spend a couple of slides validating a model and then get to the results.
Right, yeah.
And if people question your model, come back later and address the questions.
Okay, now let's call it off today,
Okay.
because it's getting too late, otherwise.
I was getting scared.
People have things to do Friday evening. All right.
How many slides do you have total number?
It's 60.
You need to get it probably
40.
two-thirds or something.
Yeah,
Keep
40.
it around 20, 25 or something like that.
I was
Maybe
thinking
30.
for 1 minute for one. I was thinking that
There's no way you can get a 1 minute.
I'm not smart enough for 1 minute.
I mean, there's so many panels in your plots. If you have one figure, there's so many panels in your slide. If you have one picture, one slide, you can probably do that within a minute. But you have so many panels, there's no way you can.
You should have like more than 100 figures.
Yeah,
Yeah,
way too many.
Thanks.
Way too many. All right, let's discuss on Monday.
Okay.
Thank you.
Thank you.
Round of applause to you. You want it long out of the Google Hangouts?
Yeah.
I wonder if the people are still there.
Thanks for the cookie. I had two.
Yeah, too.
It was a long seminar.
Is it that I'm talking slow?
That's okay. Sometimes people talk too fast. I don't think that's a problem. You just have too much material. You lost everybody.
Yeah.